set, a slight difference, slight understanding. That is the capability of ARM processor. Means ARM processor supports three types of instructions. Please remember, three types of instruction sets. Interesting nature of ARM processor is it's a multitasking processor. It means if I utilize the CPSR register effectively, I can make the processor to work in different dimensions. For example, if you change the modes, you can make the ARM processor to work in a particular mode. So what are the different modes you have, So interrupt request mode, fast interrupt request mode, abort mode, system mode, supervisor mode, okay, undefined mode, and finally user mode. All the above modes which I have mentioned except user mode are called as privileged modes. User mode is called as non-privileged mode. Please remember, privileged mode means I can have access to changing the modes. If I'm in abort mode, I can immediately step back to system mode. I can step back to undefined user mode. Likewise, and I can have access to all conditional flags. Okay, so you know how CPSR is divided into four parts: the conditional part as well as conditional flags, status, all those stuffs, execution. So in that section, so it means I have access to all the contents of CPSR if I'm in privileged mode. When I'm saying non-privileged mode, I can have the access for reading, but while writing, only writing the conditional flags I can do, but I cannot write on to the modes or IF bits. So IF means interrupt mask and uh, fast interrupt masks. So it means that setting those bits in CPSR makes the different dimension of the ARM processor. Here, an interesting nature in ARM processor is there. What is that? The one what is that called as the position in CPSR? One position in CPSR which is represented by capital T. So when we say how you are going to represent a CPSR, means you remember NZCVQ underscore NZCVQ IFT underscore mode, any mode of operation, either SVC mode or IRQ mode, whatever mode, user mode you can call it as. That is the contents of CPSR you remember. So where NZCV represents, what is that? Either the number is negative or positive, zero flag or carry flag or overflow flag, NZCV. Where Q is your synchronization bit, and there comes IFT. I and F is your interrupt interrupt mask bits, that particular bit, and there is a letter called T that played very important role in CPSR. If I'm able to change the value of that letter T, if T is 0, the T bit is 0, it means that the ARM processor making use of ARM instruction sets only. It understands ARM instruction sets and executes ARM instruction sets. So it means when the execution happens, the execution takes the ARM instructions. So what are the different ARM instructions do you have? If somebody asks, all the instruction set we till now we discussed, including data processing instructions, branch instructions, program status register instructions, or stack instructions. So all instruction sets, arithmetic instructions, whichever, all instructions will be executed by ARM processor if T bit is 0. Now if I make it T bit as 1, it means that I am making use of thumb instruction set that we are going to study now. So thumb instruction set is the fourth unit. So you can call it as, third unit. You can call it as the instruction set which is supported by uh, the ARM processor instructions, thumb instruction set. It means that I have set of instructions associated with the thumb. You can call it as thumb instruction set. So when T is equal to 1 in the CPSR, it means that ARM processor is accessing thumb instruction set. If I don't want ARM instructions or thumb instruction set, I have a J bit, that is 24th bit, I think you cross check in CPSR. If I make J bit as 1 and T bit as either 0 or 1, it means that I'm making use of Jazale instruction set when I'm making the ARM processor to work with respect to Java programming. We can make use of Jazale instruction set. 3 instruction set are possible. Now, thumb instruction set is a 16-bit instruction set. Please remember. So it is a 16-bit instruction set. It means that the instruction itself is of 16-bit. When I say 32-bit instruction, it is a 32-bit instruction set. So what's the difference? Then how the execution of thumb instruction set happens with respect to ARM processor? If somebody asks, then you should clearly mention a single word. Thumb instructions are separately allocated. ARM instructions are separately allocated in ARM processor. Whatever the thumb instruction comes in from the memory, before going, it goes with the ARM instruction decoder. Please remember. So there is an instruction decoder. While starting the process, we discussed at the start of the class, which we called it as ARM core. When we discussed ARM core, there is an instruction decoder. So here ARM instruction set decoder, there is a separate instruction decoder which converts your thumb instruction into ARM instruction of 32-bit. 16-bit to 32-bit conversion happens. Then the processing will be taken care by the execution unit. That is the ARM instruction decoder, it is called. You can search. So now how the simple explanation we must and should study, what is that? So I'll just write on few points. So the first point I can write, thumb, you can say thumb encodes. What it does? Thumb encodes a subset of the 32-bit ARM instruction. Please understand, it encodes the ARM instruction into a 16-bit instruction set. You can call it as space. It means that it encodes, actually 32-bit ARM instruction is encoded as 16-bit instruction. Why we need 16-bit instruction? The very interesting point is ARM has the higher performance. It gives me higher performance. So it gives me higher performance. Please understand, higher performance than ARM. Higher performance than ARM, okay, on a processor. Please understand, on a processor. Which processor? ARM processor. On a processor with, if I am using 16-bit instruction, I need 16-bit data bus. So data has to be carried by data buses only. We know data bus, address bus, control buses are there associated with any of the processor. So here 16-bit data bus address is sufficient. Then, but the lower performance than the ARM on 32-bit processor. But what is that? It is higher performance than ARM processor with 16-bit. It performs on a 16-bit data bus. Okay, so it has lower performance. You can say lower performance on 32-bit data bus. You can call it as 32-bit data bus. But ARM processor has 32-bit data bus. 32-bit data bus. It means that thumb instruction will not perform better because 32-bit data bus will be there. So that's what the instruction decoder converts it into 16-bit to 32-bit. So if 16-bit data bus would have been there, then the thumb instruction itself performs more. That comparison is made. What is the one more advantage of this? So wherever I have memory issue, let's say I have memory issue. So memory constraints are there. I cannot afford a memory with 32-bit storage. So it means that 8-bit storage, 16-bit storage memory constraint systems are there. Such systems are easily supported by the ARM processor. Such systems are easily supported by ARM processor, okay, using which ARM using which one? The memory constraint systems using thumb, you can say, using thumb performs better, you can say. Okay, so ARM constraint systems using thumb instruction set performs better. You can say performs better. That's the meaning. So it means that what is the meaning? Meaning is very simple. Any code you write, okay? So thumb has higher code density. You can call it as thumb has higher code density. The space taken in the memory is less. Okay, the space taken in memory is less. You can call it as like this. Okay, the space taken in memory is less. So it means that any examples if you take, so if they run any mobile phone and you can call it as a PDA, okay, PDA, any device. So code density is very important so that the memory utilized is very less and the speed will be more. In such devices, ARM plays very important role. That's what ARM processor supports both thumb instruction uh, as well as what you can call it as uh, ARM instruction set. When thumb instruction set in CPSR, if t is equal to 1, thumb instruction set is chosen. Those instructions will get executed easily. If ARM in CPSR, if t is equal to 0, ARM instruction set is chosen. So now let's compare with an example. So let's say, what is that? If I write an ARM code, okay? So you know how to write a code if you just list a set of instructions. It becomes a program, or you can call it as a code. Now in general way, if I wanted to do division, okay, division process, let's say, okay, division process I wanted to write, or a division program, you can call it as divide one number by other number. So how do you do? So what is the input I will give? So input I will give, let's say, so input I will specify r0. Let's take r0 is the register. So r0 takes some value, give some value, and r1 give r1, which I'll call it as divisor. Okay, so similarly here I will just write thumb code. If I write, just simple way you try to understand, if I write input, okay, r0, so r0 is a register, so let's take it all, it takes the value, same thing I'm writing on other side. So r1 is the divisor. Okay, so both side I declared the inputs. So what is the required thing? Output. So output means I want after division the remainder. So I want remainder should be in register. So you can call it as reminder, I'll call it as any name you can give. So I will use one more register R3 where I'll store the value called as quotient. Okay, quotient or the result, whatever you call it as. So in here also you just call if I have the output. So whatever I have taken here, one second. Uh, so just I'll put it as output, no? Output. Which one is this? R2, R2, and this is reminder. Okay, a reminder. So then I will just write R3, which is your quotient. Okay, which is your quotient. So how you are going to write a simple program? So let's say if I write a program, input I declared, I'll use the instruction move R3 comma hash 0. Please understand what is the code I am writing. Move R3 comma hash 0. It means I initialized 0. I initialized R3 with 0. 0 is there in R3. So then I'll use the concept loop. Okay. Then I'll write the loop here. Just a minute. So what I'll write in loop? Subtract S. Okay, so let me write subs, subtract S, R naught. I'll use the instructions, you just simply interpret now, R1. So then I'll say add GE, okay, subtract, add GE, okay, then R3, let's say R3, comma R3, comma hash 1, okay. So now I'll say BGE, let's say ADD add R2 comma R0 comma R1. So let's say you just understand like this. So simple program. Let's say okay. Then again loop. You can call it as loop. After the end, I'll write one loop. Let's say. Just a minute. I think this is not visible to you. Just let me write here again. So just say okay. So what is that instruction I was writing? Move R3 comma hash 0, R3 comma hash 0. So I'll write bit lower letters. So let's say loop. This is not visible, I think. So move, one simple thing, if you understand, remaining things will be very easier. So if I write hash 0, okay, so then I'll use the loop. Let's say within the loop, what I will write, let's say subtract S, okay, R naught comma R0 comma R1. Then I will write add GE, okay, R3 comma R3 comma hash 1. Okay, just understand what is that we are trying to do. Okay, branch greater than or equal to loop, this loop. Then I will, after the loop, add R2, so R2 comma R0 comma R1. If I write like this, what will happen? So if I just write on the other side the code, so what is that code we will write here? You just cross verify. So the same thing I'll start with here. If I write with thumb code looks like this. So move R3 comma hash 0. I'll write, I'll just put the loop. Okay, just say loop. Then I'll say add R3 comma hash 1. See the instruction. So now add R3 comma hash 1 is a 16-bit instruction. You can call it as subtract R0 comma R1. Okay, subtract R0 comma R1. Then I'll make use of BGE. It means branch if it is greater than to loop. Okay, after that I'll just subtract. Why I'll subtract, we'll come to know. Subtract R3 comma hash 1. So when you say this, add R2 comma R0 comma R1. So that's it. Now when you cross verify, here the instructions taken are 4 instructions. Okay, 4 instructions. Sorry, 5 instructions. Each one is 4 bytes, 32 bits, right? 4 bytes. 32 bit means 4 byte. 5 instructions are there. Move R3 comma hash 0. We know subtract s R0 comma R0 comma R1. Okay, this instruction we know. So 5 instructions are there, 5, and each one is of 4 bytes. So it takes totally 20 bytes. 20 bytes of memory. This code takes 20 bytes of memory. Wherein if you cross check here, I have 6 instructions. 6 instructions, and each one is of 2 bytes. 2 bytes means 16 bits. Each one is of 2 bytes. Okay, so it leads to what? So maximum of 12 bytes of memory location. So that's the beauty of thumb instruction set. Now you try to understand the instruction differences. Very simple. R0 and R1. So let's take R0. If I take R0 is equal to 10 as the value, some value, 10 is the decimal value. R1 I will take it as 5. So now you understand the logic. The first logic, very simple way. R3 is taken as quotient. It means that R3 is my final result. What is that? 10 divided by 5. R3 should be equal to 2 for me. That is what my result should be. 10 by 2. R3 should be 2. Remainder should be 0. R2 exactly divides. 10 by 5 means remainder it exactly divides. So I should get R2 is equal to 0 and R3 should be 2. Whether we'll cross check. What is that? Move R3 comma hash 0. This is the simple logic written. Initially I'll start R3 to be 0. So repeated subtraction is nothing but a division. So what I will do, I will take R0. R0 is 10. I will take R1 into R0. So what is subtract as R0 comma R0 comma R1 means R1 is R1 is subtracted from R0 and the result is stored in R0 only. Please understand. The result is stored in R0. It means 10 minus 5. 5 is the result. 5 is again stored in R0. After first subtraction, I'll cross check. I will add R3 with 1. So R3 becomes 1. So one time subtraction is over. That R3 is added with hash 1. R3 became now 1. 1 is moved to R3. We'll add. We'll check before adding. What is that? Greater than or equal to which one? The flag. The S bit is there. Yes, flag is set. Okay. So no, it is greater than or equal to. R0 is greater than. Yes, it is greater than. Now again I'll move back. What is that? Branch if it is greater than, again back, subtract again. What is that? R0 is having 5 now. 5 minus 5, 0. 0 means it is equal again. R3 is incremented by 1 again. R3 was 1 earlier. R3 became 2. So my result came as 2. So like this, R3 became 2. Now again it checks whether greater than or equal. Yes, it is equal. It goes back. So it does one more operation. What is the operation now? I got R0 0. 5 minus 5 means 0. R0 0. It subtract again R1. Minus 5 it has become. Minus 5. It checks. Add. So R3 is added with 1. Now R3 became 3. R3 became 3. R0 is minus 5. Now it checks. Is it greater than? No, it is not greater. Come out. After coming out, what happens? You see. What happens? R3 has got value 2 actually. Okay. R3 has got value 2. Okay. Because add only if it is greater than, otherwise no need of add. Sorry, R3 is add only greater than or equal. So R3 is 2. Then what is that happened? R1 and R0 you cross verify. Add R0 and R1. It means R0 was having minus 5. R1 is 5. R0 plus R1 means 0. R0 was having minus 5. R1 is plus 5, 0. 0 is moved to R2. That's what remainder is 0. This is how the simple division problem happened. Similarly, you cross verify here. The same operation is happened in the same sense. R3 is 0, add R3 to 1 and cross verify. Subtraction process continues. Initially, we are adding. We are not first subtracting and then adding. That's what here R3 gets correctly added. Here earlier gets it's added earlier. That's what R3 one step moves ahead. So R3 becomes 3 here. So once this procedure repeats, subtract R3 with 1 because R3 has reached 3. 3 minus 1, 2. So because R3 should be 2 only because the value chosen is 10 and 5. 10 by 5. So again same R0 and R1 minus 5 plus 5 leads to 0. 0 is moved to R2. R2 is 0 now. So both performs the same operation. Only the thing is the occupied data storage is of 20 bytes and 12 bytes. If I take a simple example like this much difference of memory storage, that's what the code density, the larger code density when performing a higher task, this thumb instructions plays a very important role. Now when I choose this thumb instruction, what is the one important point I need to know? I need to remember one important point. What is that is there must be an instruction decoder. Please remember, this is what the block I have shown here. There must be a decoder. What is that called as? ARM decoder. You can just write it as ARM decoder. So ARM decoder will takes care of this particular thumb instruction so that it can easily transfer the value. So I can show it like this. This is the instruction which is getting into the ARM decoder, and the output of the ARM decoder is nothing but 32-bit instruction. For example, if I write here the thumb instruction, what is this? I'll write thumb instruction 16-bit. If I write thumb instruction 16-bit, which an example if you take, what is that? For example, add R0 comma hash 3. If I specify, what is the meaning? I am passing immediate data 3 and adding it to the register R0 and the result is stored in R0, you are saying, but this instruction is a 16-bit instruction. How it will be converted into 32-bit? ARM decoder does that job and it gives ARM 32-bit instruction. 32-bit instruction, it means it generates an equivalent 32-bit instruction with an S bit associated with this. S bit means it is referring to the CPSR register, you know, right? So that is what R0 comma hash 3. So the instruction converted will be like this. This is how the ARM decoder does the job. Now there is a way of seeing what are the different ways I can look into the thumb flow. It means I have something like this. What is that? I can say thumb register usage. How I can use thumb registers? What are the registers available? Okay, I should know thumb register usage. Then I should know something about ARM thumb internetworking. So I need to know how there is a relation between ARM and thumb instruction and how the internetworking will happen. So it means when I write a thumb instruction, is it feasible in ARM instruction? Or when I do certain branch operations, thumb instructions to ARM instruction I can run over, or ARM instructions to thumb instruction back. So there is a link. That link we can call it as internetworking over here. So I have separate instruction set for branch instructions we are studying earlier than the data processing instructions, because we wanted to say that when I am using thumb instruction set, how branch instructions will help me to jump over to the thumb instruction set, or from thumb instruction set I am running, it means I am running the thumb instructions, how I can jump over to the ARM instruction set accordingly, vice versa. So that will be taken care by your branch instructions. That's what plays important role, when to use what type of branch instructions, how they can be written. Then we need to look into in thumb instruction, what is that called as your data processing instructions. Okay, data processing instructions. Similarly, what we have studied in ARM instruction set, there is a thorough understanding of data processing instructions. We will list all data processing instructions. We will not thoroughly go through all the things, because the similarity is there, means you know how to operate with all data processing instructions, which includes move instructions, compare instructions, arithmetic instructions, right? And what is that? What else we have? Logical instructions. Okay, so rotate instructions, all those things. uh, but when I list all those, the instructions easily you can write over, and you can easily explain with what we have seen the earlier method called as preconditions and post conditions. Using that technique, all the instructions you can easily represent by taking some values with respect to the registers. That's it, right? And here also in thumb instructions, we need to look into, interestingly, the concepts called as load store. Load store architecture definitely is associated with both ARM instruction set as well as thumb instruction set, so load store instruction set. And after that we have stack operations. You know, stack operations are very important. So push and pop instructions, which we have studied for ARM instruction set. Similarly here, how the instructions which can be pushed onto the stack and popped from the stack using your program counter register as well as link register, making use of program counter registers and link registers. And here also the lastly, which includes your software interrupts. Okay, so these are the simple study we are just making through with this thumb instruction set. Now if I list the instructions, there are so many instructions you can list. So if generally if I list, thumb is a 16-bit instruction, and it has the simple instructions like uh, add with carry. Okay, so you know ADC. I'll just list like this. I'll just write. What is that? You have add instruction, you have AND operation, AND instruction, you have what is that? Arithmetic shift right, logic shift left, LSL, logic shift right. So likewise, right? Branch instructions. Okay. So bitwise instruction set, you know. Okay. So you have branch, you have branch instruction B, branch instruction with link, branch instruction with the exchange, PLX. Okay, I mean branch with link and exchange, you can say. And BX means branch with exchange, right? Branch with exchange. So I can have CMN. What is the CMN? Compare two negative 32-bit instructions. Please remember, we are doing operations on 32-bit data only, and a few times the few instructions will operate with respect to 16-bit data. So the conversion can be done accordingly. Conversion can be done accordingly. More examples when you deal with, you will come to know how exactly the difference with respect to thumb instructions and ARM instructions. So XOR operation. So if I say subtract operation, right? And if I say LDM, LDR, when I list, immediately it will come to your mind that it's a load and store instruction. Load multiple, load single register. It means single register load instructions, multiple register load instructions, and you have LSR, okay, and LSL. So you have simple move instruction, and then you have move L, right? Uh, and you have multiply. So even I can list MVN. What is that MVN stands for? Moving the negative number, or it means noting a particular number and moving it on to a particular register. You have a negative, you have ORing, correct? And you have as usual pop and push operations. So you can list out so many so forth. What we have discussed with respect to ARM instruction set here also, ROR, SBC, it means subtract with carry, store memory location, right? It means store multiple registers, store single register onto the memory. So likewise, you can list so many, but most important point here is these instructions, which are their thumb instructions, they are a simple way to represent, and these instructions are totally different from ARM instruction set because they are 16-bit in size. This one is 32-bit in size. That is one difference. And the access to the registers, that you should remember. Access to the registers by thumb instructions makes use of registers. Any instruction given to you has to make use of register while writing a simple instruction. For example, if I write R0 to R7, I will list these registers are accessible. It is fully accessible, you can say. Accessible by whom? By ARM instruction set. If I write R8, what is that? R0 to R7 I wrote, then R8 to R12 are the registers. Okay, only accessible. Now you please understand. They are only accessible. If I write wrongly the instruction by making use of these registers, it won't execute. Thumb instructions will not be executed. Only accessible by whom? By instructions like move, add, and compare. These instructions can make use of R3 to R12. So instructions should be written accordingly. Few instructions are specific with respect to registers for the ARM. If I write R13, if I say it is always stack pointer. So limited accessibility. It means very rarely used, limited. So stack pointer, pushing and popping operations, I may use R13. They should be small, R13. Then what? R14. Okay, R14 is nothing but link register. Definitely it will be utilized, and this is also limited, not egressly, limited accessibility. Please understand the conditions what we are putting for thumb instructions. Okay, thumb instructions. LR is link register. Then if I write R15, what is R15? R15 is your program counter where it points to the top of the stack, what you are calling it as. Now it is also having limited accessibility. These conditions I must and should remember while writing my uh, instruction code, you can call it as, or instruction you can refer. And what about CPSR? CPSR, program status register, only I can indirectly access. Please understand, indirectly I can access. So it means that working with CPSR and SPSR is not at all associated with thumb instruction. Thumb instructions are not at all associated much with respect to CPSR and SPSR, wherein ARM instruction set can directly access the CPSR and SPSR by being in any mode and by using any instructions from either software interrupt instruction or program status register instruction set. They can easily access directly. Here, no, indirectly they can. Okay, but SPSR, no access at all. Please remember. So, no access at all. This is what. So now, how internetworking between arm and thumb will happen by making use of a simple T bit. That is one thing. And second thing is by making use of branch instructions. So both will together will represent in the next class. So branch instruction and thumb instruction together get me the internet working. With one or two examples, immediately we'll rush through the concept of understanding branch instructions and data processing instructions thoroughly, and realizing a clear comparison between thumb instruction set and branch instruction set with examples. How the example should be taught in taking the same kind of instructions. Let's say move rd comma rn or add rd comma rm, compare rn comma rn, something like this, or add stack pointer with immediate data. So how you are going to deal with? I need to write the preconditions and I need to write the post conditions. Who are all the registers getting affected with respect to thumb instructions? And please remember there is a small differences between the instructions. That what you need to make out the differences. For add operation, what is the instruction written in thumb and which will be converted equivalently to 32-bit instruction in ARM instruction set. So that comparison you need to understand. And remember, when we say subtract and add can be happening by making use of what is that called as shift registers, like logical lift shift, logical left shift right, right? What is that? LSR, left shift right, left shift left, something like that. So logical shift left, logical shift right, you can say. If I make use of those instructions in add and subtract in ARM processor, it is a single instruction. But in case of thumb instruction, there is no such facility of including LSL and LSR or RSR or ASR. So it means I need to write a separate logical shift left. When we'll do logical shift left, if I wanted to multiply. So in such situation, I can shift left by 2. If I say 2 times, it will get multiplied. So such kind of instructions separately should be written instead of a single instruction. That's what. Only thing is number of instructions will be increased in thumb instruction set to achieve a particular task, wherein ARM instruction set makes use of less number of instruction to achieve the task. The difference is high code density is achieved in thumb instruction. High code density doesn't mean that the code length is small. High code density means code length might be anything, but the memory occupied by that code should be less. So that is what high code density. So thumb instruction set achieves high code density, whereas ARM instruction set will not achieve that. So keeping those differences in mind, we'll work out few of the instructions similarly with the pre and post conditions, and we will study the branch instructions and data processing instructions in the next class with respect to ARM instruction set. I'll stop here. We'll see the remaining steps in the next class.
Some of the class videos have not been uploaded.
Yes.